Hello, I'm Bronis Supinski, and I'm the Chief Technology Officer for Livermore Computing. LC, or Livermore Computing, is the supercomputing center at Lawrence Livermore National Laboratory. Here I show the architecture for our two largest systems. In this slide, I give the numbers for our second largest system, which is Lassen. It is a fairly large system in its own right. On the most recent top 500, it's the number 14 system, and when it was first completed, it was the number 10 system. The basic architecture consists of two Power 9s and 4 Volta GPUs per node. We take those nodes, build them up in standard racks, interconnect them with a Mellanox InfiniBand fabric, and end up with the overall supercomputer. All right. So Lassen, the smaller of our two systems, has a fairly large number of these nodes. It's got 792 nodes. It's overall a 23 petaflop system with 44 racks. You might wonder, why am I telling you about this system when I'm here to talk about the Cerebras CS1? Well, the reason is very simple. We've entered into an exciting collaboration with Andrew's company, in which we are actually integrating, which we in fact have integrated, a CS1 into Lassen by connecting it directly into the system on the InfiniBand fabric. All right, and I want to stress that this is not just a vision. As you can see here, we've with this picture of the system being installed, it's now fully integrated into Lassen. I'd like to note that our integration team has told me that the sighting of the CS1 was one of the smoothest sightings that they've ever been involved with, and for particularly for the first time that a company has sighted something at on our machine room floor. So why are we doing this? Well, we have this vision for performing cognitive simulation using what we call a heterogeneous system architecture. Most supercomputers have the same node over and over and over again. That is what the Lassen base architecture was. But by adding the CS1, we now have a volume that is specifically tuned and intended for running machine learning models. All right, so what we're going to do is build in machine learning into our physics simulations. And there's a variety of places we can do this, from just coordinating the input to the individual simulations to many time steps, making sure things are proceeding correctly, or even very tightly integrated into the simulation and computing values that are used within every time step or few time steps of the simulation. And that's what we're looking to do. All right. Now, this raises important questions. Basically, can we have the interaction between these different volumes of the system happen quickly enough? Well, as we've already heard, there's quite a bit of bandwidth in and out of the CS1. So we've begun already looking at this, and we're actually building into a simulation called Cretan the ability to do some of the atomic physics every time step. And so what we found is that even though we need to ship a fairly large number of values into the CS1 in order to bring back a fair number of values, that the inference happens quickly enough with this CS1 that we can actually make this work. All right. We're looking at additional things like being able to update models on the fly as we generate more data from other parts of the simulation, and also potentially running the detailed physics simulation in order to be able to have a more accurate model. And again, the capability that the CS1 provides us with being able to run these large scale models is such that we believe that this will work. Anyway, that's what I have to tell you about, and I'll be happy to answer any questions over the break, or when the overall video finishes.